Hi students, welcome to another session of JEE Advanced Chemistry classes by myclassroom, and we have done already 2 in organic. So earlier we completed some physical topics and then we did the general organic chemistry, then we did hydrocarbons. Now we are going with this like alcohol phenol ethers, which is again like oxidations and reductions, the mechanistic approach, even some SN1, SN2 reactions will be there. So that mechanisms also can be covered. So this is the general plan for us. So as we are doing earlier topics, let us also continue in the same way, like taking the particular application or a numerical or concepts, then we discuss it. So let us see first one. So how many of the following reactions are correct in the given things? So let us see, we had given with all the mostly these are here, what you see is as an epoxides. So when any reactions like organic is a very important thing is how the reaction may proceed, means how the reaction mechanism exists and all that. So just to go a step by step and just think about it, then just seeing all the reactions which are there and just seeing what is given for us, then what may be the possible reaction that can happen here. So that if you just identify in the organic things, reactions, that is the major thing what exists. Suppose we added H3O plus to that, suppose. So let us consider this, means both these, all the three are mostly looking like same. Double bond is here, double bond is here, the epoxide was here. So when you add H plus to this or H3O plus, this oxygen lone pair gets protonated immediately. So the 3-membered ring with oxygen here and positive charge, there exists a ring strain immediately. So the any one of the bond around this will open now. So the epoxide cleavage happens. So this is, suppose you are saying cleaving, means only just to show that. So if you get positive charge, if it is opening here, it will get positive charge here. If it opens here, you will get positive charge here. But whatever it is, you may see the positive charge at any place that will be in conjugation with this component. So this pi bond and this pi bond and this positive charge are in continuous conjugation, extended conjugation. So what will happen now? Because if you add something here, let us say like water is there in the solution, if you add water there, what will happen is, if you add water, then what will happen is this compound will form first this OH, O, let us write like this, O, H, H plus. Then it may lose H plus because oxygen should not have a positive. Then it will convert into this form. But the ring loses aromatic character if this happens. So what is water will do? Instead of attacking that carbon or carbocation acting as a nucleophile at this stage, because the ring loses aromatic character, water can also behave like a base. So water has a lone pair, it can immediately take H plus also. So to get aromatic character, there is a hydrogen at this carbon. This hydrogen will be abstracted. So this process won't happen. Hence this way of attack will not take place because the ring is losing the aromatic character. So to retain aromatic character, water is taking the H plus. So that this sigma electron will convert into 5. So the H will come out as H plus. So that this will immediately now convert it into this form, what is given for us. So whether you open this side, whether you open this side or this side, finally it results, maybe OH will be here. That won't be that will be the only difference that you have. But we are getting phenol. So this can happen. So this is correct. So it's only just a high acid catalyzed process. How that epoxide is converted into its phenolic form. Now same, if you have NO2 and OCH3, what will be the OMe means OCH3? What is the difference that you see? The OH and NO2 groups are in para position here. Here OH and OMe groups are in meta position to one another. So how it may happen here? Suppose you consider this reaction now. In this case, what may be the condition? So just do the same thing, like again adding the H plus here, then opening the ring. So where you may get positive charge now. Suppose we have double bond here, NO2 group here. Suppose you get OH here and positive charge here. What is the other possibility that we had? You can open the ring the other side now. So we may result in this maybe. So among these two, between these two, which is more stable? This positive charge is in conjugation anyhow. Here also the positive charge is in conjugation. But this NO2 group is now acting like a minus I affecting group. So this pi bond can shift like this. So then the reaction can proceed in some other, like so pi bond can, suppose it goes here and it goes here. So the positive charge comes closer to the NO2 group. Here the positive charge comes on the correctly on this. So which is more stable among these two? That is, if you just see these two cases, the positive charge which is present at, let us say with respect to this, it at meta position. So this NO2 group cannot behave, this NO2 group cannot behave like as you say minus R affecting group and minus R affecting group here. This NO2 cannot develop the positive charge again at the same carbon. This it creates here are ortho para positions. So this is also created here. So positive charge is created here and there and here. So the same carbon is getting the positive charge because of minus R effect of this. So what will happen? This will become unstable compared to this. So what we see according to this now, this carbon with positive charge is more stable. So we will see the NO2 group is coming at, NO2 group is coming, or OH group is present and NO2 groups are present in para position because that carbocation was unstable compared to this. Now this hydrogen is acidic. Then this hydrogen can be lost. Even you get hydrogen when it is lost, you will get negative charge here. That is also stabilized by this NO2. So that you will see immediately the double bond formation between these. So this can be correct even. But with respect to like OMe, this is a reverse case. What is the OMe case maybe? You will get a positive charge at this carbon is stabilized. So positive charge may be here or positive charge may be at this carbon. But this carbon positive charge is stabilized by plus M effect of this because OMe acts as plus M effect R plus R effect. Positive resonance or electron donating group. So this is an electron with a drying group. So this is stabilized. So now this hydrogen can be lost. So this hydrogen is lost, then you will get a double bond at this. Means directly you will get this. So this is also correct. Okay. So all this, like these epoxide forms are converted into the phenolic forms in presence of acids, are catalyzed by acids. Next, let us see how many. So it is like a numerical based type. Okay. So let us see. There is again some more list. So there is, so this is 5-membered ring, 3-membered ring with the BR. So how it generally forms, where you generally come across this reaction or this type of compounds is Reimer-Tiemann reaction, where the aromatic compounds are treated with haloforms in presence of alcoholic KOH, alcoholic NaOH. Then you will see the dihalocarbene are forming, CCl2, CBr2. There they are going and reacting at the double bonded carbons. So pyridine case, so it is like maybe a cyclopentene first. It was treated with CBr2. Then it forms this. So when we added silver nitrate, the aqueous silver nitrate to this, then what will happen? The Br can be abstracted by the silver plus ion, because Ag plus will take out the Br, one of the Br, maybe you are getting a carbon with positive charge at this Br having, or this Br having any one of the halogens are having the lone pairs, that carbon positive charge is stabilized. So one of the halogen is becoming like a good living group, that may leave. And even we added a silver salt, which will immediately precipitate as AgBr. So the precipitation reaction also favors the reaction to proceed in forward direction. So one of the compound what we are getting here, that get precipitated. So what we see, first immediately with that, we got positive. But already there is 5-membered ring as well as 4-membered, 3-membered rings, which are having the positive charge already. The rings again get strained. 5-membered is okay, stable compared to 3, but 3-membered ring is unstable and positive charge is already there in it. So it's like a fused rings that exist here. So that this bond will open in such a way that where you will get a positive charge here. So this carbon-carbon bond will cleave in such a way to form a double bond between these two. So that is even what you are seeing over there. So what you see is this one will convert like 1, 2, 3, 4, 5 and 6. So you will see this carbon-carbon double bond will form, Br exists. So this is, if you just number, that is most appropriate way of opening the rings and seeing where the attachments are there, where the positive charges are there. So this is, let us say 1, this is 2, this is 3, 4, 5 and 6. So between 1 and 2 we have the positive charges. So 1 we have the Br. So we are getting at 6. So this is 1, here, this is 2. So this is 1, this is 2. So 6 is having the positive charge. So 6 is having. Now this is stable than this also, because there is even a 6-membered ring and this carbon double bonded or this positive charge are in conjugation still. So this is stabilized. So how the ring will open? Clear? So now this one can react with, now aqueous silver nitrate is there. So nitrate ion is not a good nucleophile there. So water can act as a nucleophile. So when water attacks as a, means gives a lone pair as a nucleophile, then immediately there is some hydrogen which can leave, because oxygen will get a positive charge because of oxygen acting as a nucleophile. So you can say first it acts as water attacks, then second it loses H plus, so that you will see this formation, means you will see this. So at this carbon which is having a positive, that will get finally OH. Clear? So this is also correct. So first 3 were correct. The first slide were that are there was the 3 compounds which are also true. That is also conversion is first taking place. Now this is also true. Now in this, the same thing, that you can do again. What do you see? H plus is added, nothing but H3O plus might be. So this oxygen lone pair is taking this H plus first. Then this will convert into this form. CH3s. But pi bond will shift like this. So even simultaneously, if you see this is whether it is forming or not. So this is also what you see. So this pi bond also can shift like this. So when this pi bond is shifting here, then positive charge created here. So you will see formation of this because of these pi bond shifts. CH3, CH3 and positive charge. So it is again continuous conjugation is there. But this carbon is a quaternary carbon. This carbon is a secondary with allylic position or extended conjugation that exists. Instead of that, if one of the methyl group from here, if it shifts to here. So if you see, one of the methyl group is shifted from here to here. We just see whether this is possible and write that possible structure and check whether it is stable or not. So already you see the methyl group and methyl groups here. So that methyl group, if you shift there, whatever the next carbocation that you are getting it. So how you just check whether this may happen or not. So if a carbocation is rearranging, then if it is giving a stable, further stable species compared to the earlier species which was existing. So that we will say that type of rearrangement should happen or will happen. So what we will see, this CH3 shift will take place. So you will see formation of OH, double bond is here, double bond is here, one methyl group is here, CH3 is here and CH3 is. But we will say this is more stable than this. The reason is it has still again extended conjugation, as well as because of this positive charge methyl group that exists here. This methyl group also supports the plus I affecting group as well as the hyperconjugation affecting group. So there are three hyperconjugatable hydrogens here. So in this case, there was no hyperconjugatable hydrogens. Extended conjugation was there, but the number of hyperconjugatable hydrogens are 0. Inductive affecting groups might be there, but inductive effect will not favor much or stabilize compared to hyperconjugation. So resonance effect is the dominating effect. Then the hyperconjugation is the dominating effect in the like electronic effects, because in the resonance the complete electron cloud, weak electron cloud movement takes place. So stabilization is more compared to, let us say, hyperconjugation, because hyperconjugation is also electron cloud movement, but which cloud is moving? Sigma electron cloud moves. So the sigma bond cleavage has to happen and convert into pi electron cloud. There it is a pi bond may be converting into pi bond during the resonance. So resonance effect is a generally dominating effect as we consider. So this one has resonance, hyperconjugation as well as inductive effect. So this is stabilized compared to this. Then now direct, there is a loss of hydrogen from here. So you will see the loss formation. So there is a loss of this. So this is also correct. This can also form. So this type of rearrangement also can happen maybe. Now coming to the next, which is given here, that is F. So we had a reaction, that is, if it is considered this is a ketone with amine group or NH2 group on the ring, treated with peroxide. But when you see a reaction, that is, instead of hydrogen peroxide, if you use peroxy acids, that is RCO3H, what do we see? So if a ketone is treated with peroxy acids, that is what we call the reaction as Baeyer-Villiger oxidation. So oxygen gets inserted. So if you just see this reaction with peroxy acids, so will it happen with hydrogen peroxide? No. So it can happen with peroxy acids. Clear? So now when we consider this, now how the reaction may happen. So if we consider the thing what we had there, NH2. So if it is a peroxy acid, this will happen. Then what do you see finally? C double bond O and CH3. So with hydrogen peroxide it cannot happen, but it can happen with peroxy acids. So we just see, suppose, sorry. So we are treating in presence of base condition with hydrogen peroxide. Means you may see the loss of hydrogen from the hydrogen peroxide, you will see O minus formation. That cannot easily attack at this carbon. But if it is a peroxy acid, it can attack. Okay? But in presence of acid condition you are doing. So the protonation will be there, then this oxygen gets protonated, then this carbon becomes more electrophilic, then this negative part of that peroxy acids can react at this place. So what we will see, if it is peroxy acid, R, C, double bond O, H. So maybe protonation directly you can say this oxygen lone pair attacks there. So you will see formation of this C, OH, O, C double bond O, R here and CH3, and as well as you just write the benzene ring simply NH2. Okay. So now what we see finally is this C acetate ion is a good leaving group, as this is try to leave. This oxygen gets positive charge. Let us make it clear. So this oxygen is getting empty orbital. The acetate part is a good leaving group. So which type of general peroxy acids which we use also, which are leave betterly, CF3COO, so metachloroperoxy, MCPBA, metachloroperoxybenzoic acid, if you use such type of things, where that is a good leaving group part, that may leave. So, but oxygen is getting a positive charge, so to get, let us say, stability, one of this alkyl groups here, that is CH3 or this phenyl with the NH2 group, they may shift. So, which is a good migrating groups generally. A general order is whenever we write the general migration of alkyl groups, which is a general good migrating groups. Any group which is more electron denser is a good migrating group. So, phenyl is a good migrating groups. Clear? With generally compared to alkynes, but there is some changes at some reactions. Sometimes tertiary becomes more than the phenyl, like that. But here secondary and phenyl is in Baeyer-Villiger oxidation, secondary and phenyl are better. But in a phenyl case, or methyl if we compare and phenyl if we compare now, we had these two only. If without NH2, then phenyl itself is a good migrating group than methyl group. But phenyl which is having now plus M group, NO2 plus R group, it becomes a good migrating group than the CH3. So this phenyl group migrates to this. So this phenyl part completely migrates to oxygen. So when this R, C double bond O minus is leaving, you will see completely the rearrangement happens like this. So this carbon bond is cleaving with the, means all this will happen in a cyclic transitions process. What you see the general rearrangement, what you discuss generally. So this part completely shifts. So you will see that CH3, COH, this carbon with plus now, then we see this oxygen, then we will see the phenyl group, NH2. Clear? So that now this oxygen lone pair can convert into double bond CH3, C, double bond OH plus O and NH2. Now this oxygen positive charge is stabilized by loss of H plus. So you will see finally you are seeing CH3, C double bond O So what we had earlier, that is keto with CH3 and phenyl groups, oxygen gets inserted between them. So between the C double bond O, R and R, one of the oxygen gets inserted because of the peroxy acids. So that this is an ester formation. So it's like a process of ester preparations from the ketones. But will it happen? Because anyhow, this is what you see. So now this will happen or not? No. Means this will happen in case of hydrogen peroxide case. So this will not happen in presence of hydrogen peroxide. So how many are possible for us? Here we had first three, A, B, C, D and E, which are possible for the conversion, or they may result in this. Now what we already had is phenol form. So we are adding, let us say, hydrolysis we are doing there. So the ester hydrolysis is resulting this phenol, because during this ester cleavage now, suppose you do here the ester hydrolysis, you are doing it. If you are doing ester hydrolysis, this carbon bond never cleaves. So this bond only will cleave. So acyl oxygen bond cleavage happens here. So you will see this oxygen always exists with phenol type. Means whenever you just see the isotopic effect is done. So we are starting with this. Suppose this is our 18, this is our 18, this is our 18, this is our 18, this is 18. So this 18 oxygen is existing with respect to the phenyl group. Then, so this is how that compound may result actually. That is OH and NH2. But this should happen in presence of peroxy acids, not in presence of hydrogen peroxide. Clear? So that is the condition. That's why we consider, because it is alkaline medium also. Clear? Now, and that OH is not a good leaving group in hydrogen peroxide. Maybe you will see that O minus OH formation, but because you are having a good nucleophile, maybe it reacts here. Then you may see the formation of this C, O minus, O, OH, CH3 and NH2. But here that is not a good living groups, anything, that is not a possible case. So this won't result. Coming to the next. The number of electrophilic substitution reactions among the following: formaldehyde treated with phenol in presence of NaOH. So we will say like formaldehyde reacting, there is so much like excess of formaldehyde and phenol reaction what we see, and it is resulting in the formation of what you say the bakelite or novolac. Clear? So the polymers are forming in presence of alkaline medium or acidified medium, because in alkaline medium it may be O minus. So base makes that OH phenol as phenoxide. Then the phenoxide is behaving as a better nucleophile, means better activating group. So this carbon, it is electrophilic, it reacts at this carbon. So you will see this is an electrophilic substitution. Clear? Because this carbon with a positive charge, because this phenol reacts with sodium hydroxide and forms phenoxide. But phenoxide results in this one, that is resonance structure. So double bond O minus. But this carbon with negative charge now can react at that carbonyl carbon. So it may result in this. So this will be possible. So this is what you are saying is this electrophile is attacking at this carbon. So this is an electrophilic substitution. Okay. The next ketone is there, phenol and concentrated H2SO4. Now again the same thing. What do you see? Because it is acidified condition, then the acetone is generally protonated. so that it will convert into CH3, C double bond OH plus CH3. But this pi bond shifts towards oxygen and makes this carbon better electrophile. So COH plus and CH3. But this carbon with a positive charge and electrophile, it can react at this benzene ring. So phenol is there, activating group is there, we got an electrophile, then the electrophilic substitution can happen. But this is a bulky, it can't react at ortho position, it reacts mainly at para position. So what you got earlier means first what we have seen, phenol para position is substituted by this electrophile, that is CH3 and OH. But still there is an acidified condition here. So this OH group can be protonate. So OH group can be made a good living group by acid protonation. So this OH group leaves, then this carbon will get plus charge. Now this carbon with plus charge is again electrophile. It reacts with the second molecule of phenol. Then also now again it is substituted in this phenol, another phenolic group, means another phenol molecule. So you will see this carbon positive charge or this carbon positive charge is substituted in presence of hydrogen. We will say this is also electrophilic. Yes. So these two are electrophilic. And coming to the next, this one, the phenol, and this is what we call it as phthalic anhydride, phthalic acid, phthalic anhydride. So it's just actually, if you recollect it, it's a preparation of what is the phenolphthalein. So what is this compound? We say phenolphthalein. So is it is an electrophilic substitution. So just see, then what you are seeing, phenol carbon para position, carbon hydrogen is replaced with this C plus. So it is actually acidified condition, you add H plus, then you can shift the pi bond towards this. So anyhow, this will be converted like this first at least. So this one, C double bond O, you will get a OH, C double bond O, then this positive charge, this ring opens. So this is an acid, this is a keto form, this keto carbon can react. Then again continuation, you can do it. So finally you are seeing this carbon oxygen and the two hydrogens in the phenol, they are replaced. So in the phenol, this carbon with positive charge is substituted. So this is also electrophilic substitution. Okay. Then coming to this, so this is a Coles reaction, direct. So OH in reaction with carbon dioxide in presence of alkali converts into sodium salt of this. So this is CO2, is this carbon dioxide is an electrophile in this process. So carbon dioxide or pi bond is shifted towards this like this. Then this carbon with negative charge can react at this. So you will see pi bond shifting here. So this is again also an electrophilic substitution. This is also electrophilic. Because carbon dioxide is substituted in place of hydrogen there. So this is also one of the electrophilic substitution in this list. Now zinc, dust we are using, and we just say removal of this. So it's not a substitution, nothing. We just removed that oxygen. So it is like a reduction process. So this is not a electrophilic substitution. Then this one, we say sodium hydroxide is reacting with phenol and forms phenol, because phenol is more acidic than water. So when you react with alkali, that will convert into the sodium oxide. And so you can remove the hydrogen of phenol by adding the sodium hydroxide or normal alkalis. So now what will happen? This O minus, that is phenoxide. This is nothing but what we say phenoxide ion is formed. That phenoxide ion is reacting with alkyl halides. But this phenoxide ion is reacting at methyl, so it will become like a nucleophilic substitution. So it's a part of like what you see Williamson synthesis. So this is SN nucleophilic substitution and methyl is there. So the reaction proceeds by SN2 path, Williamson synthesis, otherwise you can see. So this is okay, not an electrophilic. So in that first list, the two were electrophilic, and in this, these two were only electrophilic. Let us see. Oh, there is another list also. So this phenol with diazonium, so it is an again phenol reaction with the diazonium salt and giving red azodide formations. So this is also, so this nitrogen with positive is substituted in presence of this. So this is also directly you can say like electrophilic. Now this one OCH3 means OH is converting as into OCH3. So you will see diazomethane NH2 N2, sorry, CH2N2. So this CH2N2 results in a carbene. Clear? So phenol is reacting there. So this is also now what we can say now is a nucleophile, because oxygen lone pair or this carbene is an electrophile. So this oxygen is substituted, giving its lone pair there. So what you see there is also now a nucleophilic substitution, because this CH2 is not coming into the ring. So mostly it's only just when a ring is substituted, benzene ring is substituted with some carbon or some positive charged electrophilic species, then it should be taken immediately as an electrophilic substitution. So this is also a nucleophilic substitution. Clear? So there is some problem with this, I think, because he gave this something and this has to be like this, I think. So if it is suppose taken, this product is wrong in this, sorry. So HCHO, HCl, ZnCl2. Maybe we try to do something and same thing came here. Now what is this results just, if you see. If it is formaldehyde in the presence of acid, like what already we said reaction earlier, HCHO in presence of acid. So this will convert into CH2OH plus in presence of acid. So it generates an electrophile. So that electrophile can be substituted at ortho position as well as at para position. So this product might be given like this, you see. So OH, let us say CH2OH, let us say. But we are having acid here and even ZnCl2 is there. So what may it result later is, because this OH group is present at the benzylic position. So we had anhydrous ZnCl2, ZnCl2 is mostly anhydrous ZnCl2 and HCl. So what we see is that OH group can be substituted by Cl, means you will see this OH replaced with Cl even. So in presence of these reagents here, this will not be, this cannot be only the final product. So what you see is, this may finally converted into this form, OH, CH2. But what happened during that is, we got this electrophile which is substituted at para position. So that this also means if it is given like this, suppose OH, CH2Cl. This is also an electrophilic substitute. So each slide what we had there in the list, how many are electrophilic substitution reactions there. So we had totally now each one with 2, 1, 2, then something in the previous list. So here is these 2. Okay. So totally how many? So 1, 2. Then this 3 and 4. So not 5 and 6. So 7 and 9. So this 8th one is also not an electrophilic. Okay, that's it. So we had totally 6 electrophilic substitution reactions. Okay. Coming to this. How many of the following compounds give unsubstituted phenol as one of the products? when treated with dilute, okay, sulfuric acid. So it's actually a standard phenol preparation reaction. Based on that, it is, we can consider. So what is that is? Preparation of phenol from cumin hydrogen peroxide. So what it will give? Cumin hydrogen peroxide reaction. That is, cumin means isopropyl benzene. So we had like this. So this is only just, this is the cumin hydrogen peroxide. Okay. So in this, what will happen? Again, this is treated in the presence of acid. This OH group becomes a good protonated and becomes a good leaving group. So when this is leaving, then this oxygen is getting plus. Now what already we have seen earlier. So this oxygen with positive charge. So one of that alkyl group around this carbon, around this, that will try to shift towards this oxygen, but which is a bit good migrating group again. Phenol part is a good migrating group, comes here. Clear? Then you will see the formation of this compound. O, C, CH3, CH3, this carbon with plus. So now you can continue the reactions here. Actually, there is a OH attack later, everything, but this totally part converts now. This has H and this will convert into one of the OH is already coming. So that is finally converted into C double bond O. So you will see formation of phenol and acetone here. So during the cumin hydrogen peroxide, you are getting a ketone and a phenol. So which type of phenol generally migrates? Which is more electron denser. So which is having a plus M group migrates better. Which is having minus M group will not migrate better. So when there is no migrating, there is no a phenyl group without anything, there is a phenyl with a minus M group or plus M groups, which migrates better. So these are the cases that what we considered simply. So what we see now? In this case, which migrates? Means here what you are getting? Phenol and this. So what he is asking is phenol as one of the product without any substitution. Unsubstituted phenols you are getting. So normal phenol you are getting, not a substituted phenol. So now here it is a phenol. Now here what you will see? CH3 migrates better. So you will see finally here it resulting in this OH, CH3. So this total remaining 2 carbons you have to convert into a keto form. So what you will see is phenol plus phenyl group plus CH3. So we will call it as acetophenone you will get. Okay. So in this case we are getting substituted phenol. So this is not the list for us. Means how many you should see. So this is okay. So this is not for us. Next you will see in this. This NO2 substituted phenyl group will not shift. This phenyl group shifts. So this phenyl group shifts towards oxygen. So you are seeing this phenyl group is, this one is converted as phenol and this part is converted as C double bond O CH3 and phenyl group with NO2. So this is giving even unsubstituted phenol. Now this one, this is again minus M group. So this is minus M. So this will shift. So this also gives. Now this one, this is OCH3 plus M group. So this will shift here actually. So this completely shifts here towards oxygen. So here again it gives not a substituted phenol. OCH3 substituted phenol you will get in this case. So this is also not the case. Okay. So these 3 only. Okay. So the basic reaction that might be given, but based on that what is asked, just you have to see carefully. So this was empty slide. Now, incorrect statement regarding this following are the product of the following reaction. So what is this reaction actually refers for us? Br and OH group is there. So it is treated with silver nitrate. So this reaction, when you just see, when adjacent carbons are having a OH group and a OH group, when it treated in presence of acid, what is the reaction is? Phenol-phenolone rearrangement. So what is this reaction comes under for us is, it's a phenolone rearrangement. So where it happens? When there are two OH groups, where you treat in presence of acid. When there is OH group and a halogen group, we treat with NO, means silver nitrate. Now we can see even in presence of diazonium case, there is NH2, means a diazonium type, means you have COH, carbons here, CNH2. We are reacting with HNO2, diazonium salt formation. But HNO2 is generally can be prepared from NaNO2 plus HCl mixture. Okay. So this one, amine group is converted into diazonium salt. Then the N2 is a good living group. So there must be a good living group in the adjacent position to with respect to OH group. Then it will be a phenolone type rearrangement. So what do you see now? This Br is lost. So silver will take. So you will get a positive charge at this. So you will see OH and plus. But in first phenolone rearrangement, what is the first criteria you should follow? We always see first where the carbocation will form. But when OH groups are there, that you just check. Now when the halogen is there, halogen part only will go. When there is an amine type now, when we are treating with diazonium salt, that nitrogen will go. So this carbon which is having NH2 group will convert into positive charge first. So that will form a carbocation there. But that carbocation is stabilized, or maybe rearrangement takes place because of stabilization can happen. So one of the alkyl group from here to here it will shift. So here also there is rings now. So around this carbon which is having the OH group, these carbon bonds will break. So this carbon bond anyhow is linked. So this carbon bond or this carbon bond will break. But this carbon bond, when it breaks, this carbon goes and attacks here, it forms only a 4-membered ring. But this carbon bond, if suppose cleaves, this CC bond, this carbon getting the negative by cleavage like this, this carbon if it goes and attacks at this, then it forms a 5-membered ring at least. So ring contractions can happen also. So there are some possible cases where the ring contractions happens. So this is one of that case. So what you will see? So this one is a 5-membered ring. This one is again another 5-membered ring now. So if you just numbering it, otherwise you just see this CC bond cleaves, this C and this C bond forms. So you have a 5-membered ring like this, suppose you just write like this. You just link, because there is a common carbon for both. So this carbon is a common carbon for this 5-membered ring and even for this 5-membered. So you can just write like this. So this 5-membered ring and this 5-membered already which we are seeing. Clear? So this C 1 2 second carbon. So you just assume this is 1, this is 2. So you have OH here and plus. Now this will convert into double bond. That is phenolphthalein, keto form. So this will be now giving this one as a final product for us. So what is the product in this process for us? Is a double bond over here. So now it will give a color precipitate with 2,4-DNP. So aldehydes and ketones will react with 2,4-DNP and will give a positive reaction. So this is okay, correct. Because it will be now cumulative. You can't say it's a carbonyl reactions now. Okay, because we already seeing the all topics. So this is maybe we are discussing in alcohol or glycols or these one. But maybe you don't take up at that stage 2,4-DNP reaction, but now we can't say that. So it can react with 2,4-DNP, but what we need is incorrect statement. So this is a correct statement. Statement is correct. So let us pick like this. So this is it your option? No, this is not our option. It gives an effervescence with sodium metal. So do we have any acidic hydrogens here to give a acidic sodium metal reaction is nothing but it liberates hydrogen, effervescence. So hydrogen gas is liberated with effervescence. No. So this statement is wrong. Statement is wrong. So your option. Next, it reacts with lithium aluminum hydride will give a product which gives red coloration with ferric ammonium nitrate. So if you react this product with lithium aluminum hydride, this will convert into alcohol. In this C double bond O keto group converts into alcohol. But what is that alcohol is now? Secondary alcohol. Okay? So this one, if you just see. So without positive charge, if you just see. So if you are reacting with lithium aluminum hydride, this will be the product in this case. But secondary alcohols and primary alcohols will react with ferric ammonium nitrate, CAN, and will give red color. So this is also statement is correct, but not our option for us. Next, it is achiral initially now. So this is now an achiral molecule because there is no chiral carbon here, but becomes a chiral on reaction with NaBD4 and ETOD. So what you will see with that is now when this is treated with, so just go into the next page because we have enough space also there. So you have this 5-membered ring, keto. We are reacting with NaBD4 and ETOD. So first sodium borohydride will give deuterium, then ETOD, that is isotopic of enol. So now this one will give D plus. So this will convert into now this way. So D will get and OH or OD. Sorry. Now this carbon is a chiral carbon. So this carbon is a chiral. So it becomes now optically active. Clear? Because at this carbon you have D and OD. This carbon chain is different. This carbon chain is completely different. So this carbon having chiral nature now. So this will become optically active. So as far as the given thing, this is also correct because earlier it was achiral. Now it becomes chiral after the reaction. So this is not our option. Okay, done. Clear? So we'll go with the next. Match the molecules of the column 1 with the reagents with them in the column 2. So let us simply see what will happen at this. Reaction with concentrated H2SO4 means it will react with concentrated H2SO4. Means only just this is our alcohols now. So what is this alcohol is? Tertiary alcohol for us. Let us write. This is a tertiary alcohol for us. The tertiary. This is primary. This is tertiary, but this is secondary. Because the reaction when you just see the getting dehydrated or dehydrogenated with copper metal. So this part is clear. Given compound, so these are the just see. So given compound or product obtained by the oxidative cleavage of HiO4 gives yellow precipitate with I2 and NaOH. Means if you are reacting with HiO4 and you are getting a product, means the product of this reaction you are taking. Means the product in the sense given compound or the product obtained by oxidative cleavage. So directly you can take this product or you can take the anything, maybe with the other options it may be. Because HiO4 cleavage happens only in this case. Because this is a normal alcohol, this is a normal alcohol. So it is a glycol or in a carbon having a COH and OH in adjacent positions, or vicinal diols you can say, or C double bond OOH, then the peroxide cleavage can happen. So here what we see, so this compound only refers maybe this one, but anyhow he referring with all the cases. So giving a yellow precipitate means it's nothing but a haloform reaction maybe. Otherwise iodine is there, iodoform reaction, which is only used as a characteristic test. So which is giving an yellow precipitate maybe there. So turns acidified dichromate green, decolorizes alkaline cheminophore, means they react with that. So dichromate will behave like an oxidizing agent. Acidified cheminophore is also behaving as oxidizing agent, strong or alkaline, sorry. Even alkaline as a cheminophore is an oxidizing agent. So now what you will see? So this is secondary, this is secondary. So now all the reaction might be related to your alcohol properties. So picking this first, can it react with concentrated H2SO4? Any alcohol reacts, means any alcohol can undergo dehydration, and finally anyhow it will give right surf product always as major products. So when you are reacting this compound with concentrated H2SO4, so you will see the OH is last and double bond you will get here. So maybe the questions can be asked how many alkenes you can get there, that also you can see. So you can see double bond formation in alpha positions. Okay, so this can react. So first one you can say suppose A. So I can say this is P stands for this. So just apply all this with respect to this first. So it reacts with concentrated H2SO4. Okay, it gets dehydrated or dehydrogenated with copper. So we have a specific reaction with copper. Primary alcohols will give aldehydes, secondary alcohols will give ketones, tertiary alcohols will give alkenes. So tertiary alcohols undergo dehydration, whereas primary and secondary alcohols undergo dehydrogenation because it is an oxidation process. So there is a loss of hydrogen. So this can be dehydrogenated. So Q also. Now this compound will give no haloform reaction because it will not give a ketone. Then next, it's a cleavage. You can't do cleavage also with pyridic acid. So this also will not work for this. Acidified cheminophore cannot oxidize this tertiary. Decolorizes is not there with cheminophore also because cheminophore also cannot oxidize tertiary. So only P and Q. Now let us apply in this. Can it react with acid? Yes. So everywhere it comes P. All are alcohols, anyhow acid reacts. It dehydrates, so it's a primary. Q also comes. Now can it react with now HI, means can you cleave this? No. Can I directly react with now directly with yellow precipitate? Will it form with sodium hydroxide? No. I2 in NaOH? No. So R will not be there. But primary alcohol can be oxidized by dichromate as well as with the alkaline cheminophore. So S and T will work in this. Now in this compound can react with acid, can be dehydrated, dehydrogenated. So you have tertiary as well as secondary. If tertiary may be happening, secondary can happen. So what do you see? This can be possible. If this compound is directly or reacting, may not give iodoform. But if we cleave it, so what is the product that we get from this? Pyridic acid cleavage, Me and OH. When you cleave this one with pyridic acid, HiO4, so you will see this carbon, means pyridic acid, you just insert the OH groups at both the carbons. So if you just see OH is already there, it was converting into another COH. So that you will see that will convert immediately into a gem diol. The gem diols are unstable, they immediately lose water and they will convert into C double bond O. So directly convert this C into double bond O, this C into double bond O. So you will see Me, C double bond O, CHO. So this is the product with HiO4 reaction for iodic acidic cleavage. But can it give iodoform reaction? Yes. We have C double bond O Me. It can give iodoform. So it will give I2 plus NaOH. It will give CHI3. Okay. So for this also R works. So can it react with acidified dichromate? Tertiary was there, it won't. But secondary is there, it can be oxidized. So S. So decolorization you will see because KMNO4 reacts. So acidified dichromate will convert from reddish brown or R to green color because of chromium converting from +6 state to +3 state. So that is a characteristic reaction of dichromate. With the KMNO4 in alkaline condition it changes to +6 or depend on M. Change is 1, N factor is 1 or N factor is here 3. But in acidified condition it changes to +2, N factor is 5. So what is this is both these possibilities are there for this. Next, this is secondary alcohol. So P first, it gets dehydrogenated Q. Directly you can react this compound with I2, it will give iodoform because alcohols which are secondary alcohols with iodine in presence of alkali first get oxidized to keto forms. So that it will form C double bond O Me there. That C double bond O Me can react now. So R also works for here. Then it turns green. This turns decolorizes. So it is PQ, this is PQST, this is PQRST, this is PQRST. Okay. And coming to the next. In which of the following cases the particular, all these are ethers, no, where you can't prepare by Williamson synthesis. So what is Williamson synthesis says? Williamson synthesis says alkyl halides are treated with alkoxides, sodium or potassium alkoxide will form ethers. But the reaction majorly proceeds by, not majorly, proceeds by SN2. So which reactions will favor by SN2 is an important thing. So which will favor? Your alkyl halide should be less bulky. So this alkyl halide can be generally primary or methyl or primary or to some extent secondary. But it should never be this alkyl halide or should not be tertiary. So the bulky group, if it is there, suppose means you have CH3, O, CH3, CH3, CH3. Where you can write this R simple cases. This is CH3X. This methyl part should be there in all alkyl halides. Then alkoxide should contain this bulky. Because if tertiary exists in the alkyl halide, it will favor E2 but not SN2. So anything which is a bulky alkyl groups are there, that should be there in the alkoxide but not in alkyl halide. So here, this part can be phenolic, phenoxide, then this is prime benzyl. So this can be possible because benzyl will favor SN2, allyl will favor SN2. Clear? But in the phenol halides, you can't substitute O, R. So we can't do the substitution in phenyls halides. The halogen cannot be replaced. So there is a specific condition. There is an electron with the drying groups must be there in ortho para position. Then only the phenyl halides, aryl halides can undergo substitution reactions. So you can replace it. So here if it is alkyl halide, phenyl halide here you can't do. But so you can have X here, you can have NEA here. Then it happens. So this can be prepared. But both the sides when phenols are there, you can't cleave any side, you can't do this is alkyl halide or this is alkyl halide or maybe phenyl halide. Then oxide, that you can't do. This cannot be possible preparation. This is vinyl, this is vinyl. No. Because vinyl or vinyl and aryl or phenyl halides cannot undergo substitution. Because the carbon halogen bond will have a double bond character. This is allyl, this is allyl. Okay. SN2 favored. This is secondary, this is isopropyl. Okay. To some extent, but a major part you may see the alkene also maybe. In this is CH2. So you can say this part as ONA, this is CH2, Me, means ethyl. So this is okay. So this is H, this is Na. This is the better way. In this case, it is anyhow symmetrical. So this is also okay because it is a primary. So this is, don't see this is into. I mean, it is a halogen. So X is representing the halogen here. So this you can't prepare. So now what you can do in this? So if you just cleave any side, it is a tertiary part. So you can't prepare this. So in this is tertiary, this is secondary. So to some extent, but this is anyhow will give the major as an alkene. But this can at least will form to some extent. But in this cases, you never see these compound formation. So here there is at least some possibility of this ether formation. But the major product here is also alkene only. So in this case and in this case, the major products can be alkenes again. So here you can, because you just bring. Okay. So we can prepare. We can't prepare, it's not a, we can prepare, but it's not a major product. Okay. So these are the cases. Coming to the next. Correct statement regarding the product of the reaction. So just you see this type of oxygen things. It's an acetal type. So this carbon, which is actually if you see. So a simple way where you will see the acetal types maybe. You have a carbon, immediately there is an oxygen with an alkyl group. At this carbon there is immediately oxygen and alkyl groups. Then it may be a acetal. So this is C, O and carbon chain is it. O and carbon chain. Means this was actually your carbonyl carbonate. But what is that carbonyl carbon? There is a hydrogen here. So it is an aldehyde maybe. Now you are cleaving, suppose with water now completely by heating and you are cleaving. What will be the products for us? You will get these are the products. So you are cleaving this O. So you are just breaking this. So acetals can be converted finally back into alcohols and aldehyde forms by hydrolysis, adding water in excess. So this can be done. So this is converted into alcohol. This part is converted into alcohol. This part will convert into keto form. So here you are getting H and OH. Here also H and OH. So this is converted into keto form. Next, this part also, you can't cleave this carbon bond. So ethers, when you just even use that, the oxygen and phenyl carbon bond we can't cleave. Because even that oxygen lone pair is in conjugation. That carbon oxygen is double bond character. So what you see? Here also you can cleave. So here you will get a H and OH. So what was actually we are getting finally, if you see, it's OH here, plus this is CH2OH, this is CHO effectively. So it is CH2OH and CHO, plus this part is nothing but CH3OH. Now let us see options. So what we need to pick, correct? One of the products turn neutral FeCl3 into violet. It's a characteristic reaction of phenols. Phenols will give violet color with FeCl3. This is correct. One of the products give failing test. So failing test can be given by aldehydes. So there are some specific conditions. Formic acid also can give. But this also can give. Tolerance reaction, Fehling's reaction, Benedict's test. So this is also correct. All the products turn blue litmus to red, means they are acidic, are acidic than water. Phenol is acidic than water, but methyl is acidic than water, but this alcohol is not acidic than water. This OH and aldehyde part is there. So alpha hydroxy, clear? So because this carbon is a functional group, this become alpha carbon. So this is alpha hydroxy aldehyde. This alpha hydroxy aldehyde is not acidic than water. So methanol is an only exception in case of alcohols, which is more acidic than water. So that also can give, or that also can convert, turn clear into red color. So which are acidic. So all products cannot convert. So this is the wrong option. All the products evolve hydrogen on reaction with sodium metal. So wherever there is some acidic hydrogen, so that will give. So alcohol hydrogen also can liberate H2 gas. So this can liberate anyhow phenol. This is alcohol, it can liberate. This can liberate H2. So this is also correct for us. Okay, done, I think. Clear? See. So just mainly first cleavage part of this. So you can do the mechanism thing and everything. Correct statement regarding the following reaction. So MgETO, ET2O, so diethyl ether, dry ether. So it's nothing but a formation of Grignard. So this alkyl halide bromide will immediately convert into a Grignard part. But already nucleophile you are getting, nucleophilic carbon you are getting. This carbon becomes nucleophilic. But this carbon, which is now already electrophilic carbon. So when there is an internal nucleophile and electrophiles, they immediately react. So intramolecular reaction favors. So this carbon with negative charge can react at this. So what we just say directly now, what is the final product that we get now? That is, there is a ring formation now, 1, 2, 3, 4, 5. But this carbon, which is having a particular geometry there, particular orientation there, that cannot be affected because this carbon only reacting here. But what is this reaction is? It's a nucleophile. This is an electrophile. It's a planar. So that carbon can attack from the top, carbon can attack from the below. Means above and below. So the orientation of this C can be affected. Electrophilic, planar. So the CH2 minus can come, means this was CH2 minus. This CH2 minus can approach like this. This CH2 minus can approach like this. So there is two orientation that is possible at this carbon. If it is becoming chiral, then only you have a particular effect of this. Otherwise, there is no chiral nature is coming, resulting it, there is no problem for us. So this is 1, 2, 3, 4, 5. So you write a 5-membered ring. So what is numbering system? So this is 1, this is 2, this is 3, this is 4, this is 5. So that Br was lost anyhow. Our OMG Br exists, then water we added, we will convert that into OH. So what is first one? Has a methyl group and OH. Second carbon, third carbon, fourth carbon has methyl group and hydrogens in. So, but this one results in 2. Means you will see this CH3 can be above, OH can be below. You can see another one, that CH3 can be below and OH can be above. So here the CH3 and hydrogen position will not affect. Okay. So what will be this? We have two chiral centers here. So this is a chiral carbon. This is a chiral carbon. Because already that is a chiral. This carbon is already chiral. So we considered some orientation carbon. Now we are getting this. But these two will be like enantiomeric type. But these two compounds totally will become like now diastereomers. Because at one carbon, if it is changing, at other carbon, if the orientation remains same, they become diastereomers. So what are these now? Let us see. The product is an organometallic compound. No, we don't have any organometallic compound. We got organometallic compound, but internal reaction was there. Because of that internal reaction, that organometallic compound is not existing finally. The product is a mixture of two isomeric compounds. Yes, these two are isomers. The product gives an equimolar mixture of two diastereomers. Yes, because this carbon attack from the above or below is equally same at this planar carbon. So it CH2 minus and approaching and CH2 minus approaching at an equal extent in both the ways. So these two will become equal in proportion, 50% of this, 50% of that. So this is also correct. So you will get an equimolar mixture of diastereomers. Next, the product is a chiral keto. So we don't have any ketone part in this. Okay. So if we assume this is CH2 minus is there and you added immediately plus, then this may become chiral. But there is an internal immediate reaction and water is added at the later stage. So this is not you can consider. Okay. So this product is a chiral. Clear? Now let us see anything is there just to some time. Okay. So there are a list of reagents are given in the table. So first one, second, third columns here. So which of the following sequence of the reagents may convert cis pent-2-ene into mixture of 3 or more isomeric carboxylic acids? Okay. So let us see what may happen if the reagents are taken for the cis pent-2-ene. So what is cis pent-2-ene if you write? So cis so pent means 2-ene. So this carbon is supposed to. So you have a methyl group here. There is hydrogen here. Then there is again a continuous carbon chain here. Pent-2-ene. So this is H. So this is a carbon chain. So 1, 2, 3. So this is C2H. So this is cis pent-2-ene. We are converting into a mixture of 3 or more. You have to convert into 3 or more. Which type, which list of reagents, conjugation, addition of 1, 2, S, 2, 2, S, 3, 1, S will convert into that. Let us see. First, taking with this options. To take first one, add HBr to this. So adding HBr to this, what it will give? Adding HBr to this will give. The addition of HBr can happen here or here. So you will see CH3, H. So Br may be here, C, H, H, C2H5. Or because the carbocation here or carbocation here is more or equally stable, you don't have that much difference. So it is CH3, C, H, H, C, H, Br, C2H. It results in two halides. Then reaction with 2 again. What is 2? MgETO. So again Grignard part you are converting. So the Br is converted to MgBr. This Br is converted into MgBr. Then reaction with S. What is S? CO2 hydrolysis. So you will do CO2 reaction here. So CO2 reaction there, because it was Grignard part at that particular stage. So what is your final products with the reactions here? Is you will see CH3. So if you just see this one reaction here, this one reaction first with MgET2O, then reaction with CO2, then acidified H3O plus. What we will see? This CH3 H, but CO2 approach again can be two directions, like what we said is Grignard reagent can approach. So at this carbon you can see COOH, the CO2 and COO minus, then it is protonated. So you will see CrH2 HHC2H5 or C3H7 you can write. But at this carbon you can see 2 chirals, not at this. So this carbon CO2 is attacking, but here you don't see any chiral things that is coming. So this is one product. Then this can be obtained. So you can get 2. Clear? So you are getting in this case. Next, suppose 2,2S, NBS reaction with this. NBS also you are doing allylic bromination. So at this carbon or at this carbon radical will form. So at this carbon it is better actually compared to this. So here again you can see CH2Br, or this carbon hydrogen can convert into that. Means if it is NBS reaction here, what you see is this is giving 2 products here. CH2Br, H, CH2 or C2H5. What is the other one that you get here maybe? That is, you can see this one, I think. So just write one more product here. C double bond C, H, CH3, H, CHBr, C2H5. Okay? So what are the possibilities? 2, this is one, next 2, next reaction. So this will convert into halide, this will convert into halide, this will be CH2COOH, this is CH2. So 2 or more you can get carboxylic acids. So this also can be correct. Clear? So these 2 are correct here in this case. 3 or more, sorry, 3 or more you have to get, sorry. So I think 2 are there, see. So 2 you are not getting in this. You are getting 2 only. Because Br addition can be here or Br addition can be there in this. 2 products are formed. Then after that nucleophilic attack, but CO2 part is not giving. Clear? So here also CO2 part will not give. Okay? So only two products you will get in this. So 2 products you will get in this, 2 products you will get in this. So let us see the third case. HGOAC H2O means we are converting into alcohol mostly. Then reaction with sodium borohydride. So it is overall process is alcohol preparation. So you got an alcohol at this. So addition of this will give an alcohol. Okay. So just if you see, we will just clear this, then we go there. So what is cis? C double bond C, CH3, H, C2H5. Reaction with this 3 and 1. What it will give? Alcohol. So you see C, H, CH3, OH, H, C2H5, H. Or you may get even this C, H, CH3, H, C, H, C2H5, OH. This more or less same in this case. Now, what we did is S. So, with the CO2. So, alcohol reaction with CO2. No. So, maybe this. Fourth, B2H6 alcohol you are getting. Then reaction with P. So, alcohol is reacted with now the means ketones. So, you got same alcohols. So, it may be like what is the this is what you call OMDM. This is HBO, but this is peroxide, means anti-Markovnikovs. But here CH3 reaction with alcohols. So, alcohol reacts there with the CH3, then CH3, this CH you will get as OH. Let us say anyhow protonation was done. Then you will get this alcohol part, O, that part you will get. Means this R, you are getting alcohol part. So, you are getting here, this is giving a chiral carbon, because our attack was two ways. So, aldehyde carbon, which is a planar, alcohol can react at 2. So, you will get 2. Then after that, you are reacting with the, let us say, what you see, I2NaOH is converting into alkoxide. So, it is also resulting in mostly 2 cases. He is asking 3 or more. Mixture of acids. So, it is an alloform reaction later on. So, where you will see a carbon cutting chirality there. So, this carbon was becoming chirality. So, this one only can give, because this carbon is a chiral carbon. So, you are getting 2 chiral centers there coming it. So, this is only resulting in this. Okay? Should result in this. So, this is the thing. So, alcohols we done little bit. So, revising the different reactions there, attacking of alcohol, forming acetals and peroxy acid, means HiO4 reaction, Grignard reaction, applications little bit. So, I think this will help you for revising the things. Okay. Thank you. We will conclude with this. We will see in the next. Okay.